Okay, so good evening. My name is Andrea Zanoni. I'm from Politecnico di Milano. My job this evening is to ease you into the final portion of the workshop with a nice technical presentation with equations. I will promise you, though, that they are not essential for the discussion. What I will be talking about, let's get straight into the matter of things, is our approach at Politecnico Milano in my research group to numerical modeling and simulation of Rotorcraft pilot couplings phenomena. So first of all, I have to define the overall meaning of Rotorcraft pilot couplings in our perspective. And so first of all, we can think about the pilot action on the aircraft, on the Rotorcraft in our specific case, as being composed by two parts. The first one is a voluntary action, that is the control action of the pilot to follow the desired trajectory, for example. And the second one is an involuntary action that is only due to the mechanical properties, the biomechanical properties of the pilot body. And the second action here is activated by the aircraft accelerations, of the cockpit acceleration that are transmitted through the pilot body to the actual control inputs. Okay, we focus on the second part. Rotorcraft pilot couplings can be intended to relate also to the first one, but we generally, for in our research group, we focus on the passive actions, voluntary action. So just to understand that the problem might be there, in this picture, you see represented the, let's say, common values for the natural frequencies of various components in various colors. In yellow, instead, you see typical natural frequencies of the human body. And you see that you have some overlapping. So just by looking at where the yellow lines stand with respect to the other colored lines, which are the aircraft modes, you can see that there might be some interaction. And especially in some areas, that interaction can be critical for the control of the vehicle. What we see down on the lower part of the slide instead is a feedback loop exists between the aircraft and the pilot. Pilot acts on the insector rotation that through the control chain are transmitted to the swash plate. From the swash plate, they go to the main rotor, obviously, and the main rotor will generate loads that they will be transmitted to the cockpit and the cockpit back to the pilot again. That will basically act in a, let's say, control system modeling approach, if you want, will act as a filter. Okay, and there's a transfer function between the acceleration at the cockpit and the involuntary control input. So we focused on kind of events that, as I was telling before, are characterized by the involuntary input, which goes under the name of pilot-assisted oscillations. Okay. Voluntary part of RPC is generally called pilot-induced oscillation, or PIO. Okay. We focus instead on PIO. And let's say the main driving quantity that is important in this context is called the biodynamic fit-through, which is the transfer function that I was talking a few seconds ago between the accelerations and the control. So here I have collected a couple of extracts from accident reports that mention specifically some kind of PIO during the having, let's say, an impact on the accident. The most prominent one, probably the most recent one also, is the one of the Bell 525. And in these reports, actually the feedback loop that sustained the unintended control inputs of the pilots in the collective chain, command in this case, was specifically mentioned in the report. So the problem is there, and we need to understand better what drives it, how we can tackle it, and how we can produce in the end design recommendation to avoid it. So our approach is mainly devoted to the numerical modeling and representation of the pilot biomechanics to, first of all, estimate from first principles the biodynamic filter. This is a rather challenging transfer function to estimate because it depends on a plethora of parameters. Pilot body type, for example, you can see up here some experimentally identified curves, which in this case are related to the roll control input due to lateral acceleration. And you can see here for 3 different test pilots, the 3 curves have significantly different shape. Okay? You can see that there is some input that, some difference that is related not to any external parameter, just to the body type of the pilot. Then we certainly have influenced by the body pose, so how the pilot is actually holding the commands, kinematics, muscular activation. This is also related to body type in some sense, but separated in some other. The task that the pilot is performing is actually having a great impact. Also related to the task, the pilot workload that is needed to perform the task. The inceptor's characteristics, which might be represented by shape, trim, balance, and spring, their inertia, lever length, whatever. We can go up and go on and extend this list a lot. The classical approach for this, I say classical because there are some examples in the literature dating back to the late 80s for the first, let's say, experimental approach to this problem, are, as I say, purely experimental. Let's build up a test bench. Let's shape the pilot, measure the output at the commands, and then use the result to drive the design. This can be acceptable if the problem would be a spot one, say on one single machine and on reference conditions well defined. Obviously, if we change the reference condition, those transfer function will change and we lose the experimental data. So what we did instead is to start from first principle and to get into the modeling of the pilot biomechanics. So our approach is based on multi-body modeling of the full upper body of the pilot. We have been developing multi-body models for the upper limbs and the spine, so the complete upper body now, for the last 10 years at least. And this is the state of the art of what we got to. It's a combined model. Actually, there are 2 different models for the upper limbs and the torso that can be combined if needed, or they can be simulated separately if not. Also, the upper limbs model can be used in full configuration, so also with scapula and clavicle, or we can remove those 2 and have just a spherical joint between basically the humerus and the rest of the body, which is usually the case for the case that interest us, because the shoulder will not be moving a lot during piloting tasks. And we developed also the tool that we use to simulate this model, which is called MBDyne. It is free and general purpose multi-body dynamics software. Once we have the model, though, we have to adapt it to represent a specific pilot, but not in the sense that we want to represent a single person. We want to represent one pilot starting from its anthropometric data. Let's say the most probable pilot that has the age, stature, BMI, and gender, for example, we want to reproduce. So we are not tied to a specific person because we target conceptual design, for example, stage, so stages in which we can take actually meaningful design choices in our system. So we don't want to be tied to a specific person and have to measure and reproduce the model. Starting from basic, let's say, anthropometric parameters, we generate the most probable geometry. In this case, we start from the rib cage because we found a very interesting and easy to use model of the geometry of the rib cage, which was parameterized by the parameters that we are interested in. And starting from then, we then go to build the full model with linear regression equation that gets us the second length, the scaling equation that can give us the inertial parameters and the stiffness and the damping parameters of the complete upper body. So starting from this generated data set and model, we start to assemble the model into the standard anatomical position, which is the one shown in the figure. Then we have to perform a first step, which is an inverse kinematics one. Starting from this pose, we have to move the model into the piloting, say, position. So make the pilot actually grab the command. And here we find the first problem, let's say, solving the model, because the inverse kinematics is an underdetermined problem for the upper body. We can impose 6 degrees of freedom of the ends and still have 1 degree of freedom, which is height basically of the elbow. So we solve this by an original approach directly at position level. Then we can move to inverse dynamics to estimate the muscular torque, the articular joint torques that are needed to perform a certain motion or to just keep a standing position, a reference position. We estimate by another underdetermined, well, in this case, overdetermined problem by solving an overdetermined problem, the muscular activation. Each limb is, if you want, can be related to a manipulator which is overactuated, in the sense that you have multiple muscles doing the same job around the single articular joint. So we have to distribute the muscular force in a sense that, in a way that is meaningful, and we do that by optimization, and usually just seeking the minimal total activation. Then we can move to a direct analysis. In this case, we transfer the reference torques and length of the muscles to a direct dynamics model. We impose generally the acceleration at the cockpit base, and adding a flexible part of the activation that muscular activation that we have estimated in the previous step. So basically, we add a very simple PD controller to each muscle to keep the reference length in the most simple case, or to track an history of muscular length, reference length during a transient simulation. And here the output is actually the interactional dynamics between the pilot and the helicopter system. So what we can get out of our simulation is, here is a first example. In this case, we are looking at 2 different pilots. One which is a little bit shorter, 1.65 meters height and 78 kilos. The other one which is a little bit taller and heavier, 187 by 87 kilos. Same reference conditions for collective lever length and mass. And you can see that just by varying the aerodynamic characteristics, so the anthropometric characteristics actually in this case of the pilots, the static gain damping ratio and natural frequency of the biodynamic fit-through function are changing. Okay, so for example, let's pick the static gain. You see that as the collective lever input is increased, for the 2 pilots, we have 2 different curves. Okay, in which the static gain is following. Okay, the different reference conditions. Then you see 2 families of curves here, which are in trim-off conditions and trim-on conditions. Okay, 3 trim springs active or not, and you can see that that is another system that has a very strong influence on the interaction there. Second example is basically same as before, but with very different parameters. Here we are picking the one pilot and we are changing the characteristics of the levers between what we call the short and light and long and heavy. The other kinds of all considerations can be done here, but the general things to bring home is that there are some pretty strong differences in the biodynamic fit-through due to all of these parameters. So let's make it a step further, and let's see how we can close the loop and to have some meaningful information about the closed loop system, the complete system pilot and helicopter system. We choose to, in this slide, I choose to show you the most basic example that we can do. We are focusing on the collective command and collective input channel. So the most basic helicopter model that we can use is this one, which is just the heat dynamics equation and the Koenig angle equation coupled together with a very simple representation of the collective state here. So with these 2 degrees of freedom model coupled with the biodynamic fit-through that we estimate on the nonlinear model, we can have some we can estimate the stability of the closed loop system. And we're going to look at the stability through the Nyquist diagrams. I don't know if you are familiar with them, but if not, no problem. So you very briefly, we can evaluate the stability of the closed loop system. And varying a couple of parameters of interest. So first parameter that we wanted to explore, the variation of which we want to explore, was the total mass of the helicopter. In this case, was varying between 0.9 and 1.3 of the reference mass of the machine. And okay, you see that the closer this branch of the curve is going to this dot, the closer we are to stability. Okay, the reference system is unstable because the curve passes above on this side, on the left side of this. Okay, but the closer we get here, the closer we are to regaining stability. Okay, at varying the parameter. So in this case, as we increase the mass, the curve goes to this point, and in this case, we can say that adding mass, say increasing the mass of the helicopter is actually beneficial to the stability. Why? Because adding mass is reducing the acceleration. Okay, so the input to the pilot is reduced. An opposite trend instead is found by varying the main rotor angular speed. In this case, we vary the value between 0.8 and 1.2 to the reference conditions. And instead, in this case, we have 2 combined effects. The first one is we move the Koenig mode frequency away from the vertical bounce range. So we have a positive effect on this aspect, but we have a negative effect that comes from the increasing the rotor loads. Okay, with the speed. So in the end, the net result is that we worsen things by augmenting the rotor speed. If we let the Koenig mode frequency vary instead, we are obtaining a positive result, which is the same as varying basically the main rotor speed without the negative effect of augmenting the loads. So we are moving away the Koenig mode frequency to the natural frequency of the pilot. Okay, by the so we are decoupling the 2 systems, and we have a positive effect on stability. Last parameter that we evaluated was the varying the collective stick mass. In this case, adding mass to well, actually, decreasing the collective stick mass has a positive effect on the stability margin, but this is not, again, let's say, sufficient in this case. Well, let's say 50% variation in this case was not sufficient to increase stability. The general trend. Last part of my presentation is instead related to experimental activities to support the numerical modeling and the development of let's say, the new path that we want to follow in our research. The first one is an activity that we performed in 2018 with the help of Leonardo helicopter at the AWARE flight simulator, with the help of Captain Andrea, which was the pilot subjected to the test. A very patient pilot subjected to the test, because we asked him to wear some motion capture markers and EMG sensors, which are sensors that can read the muscular activation. And so it was not exactly a comfortable afternoon for Andrea, but it was a very productive one, fortunately. Well, the simulated scenario was deck landings on Sirio class frigate. And I have to mention that Andrea is an ex-Navy pilot and has a very extensive experience in doing these kind of tasks. So these results are general in some sense, but specific in other sense, because of the experience of Andrea. What we saw was, first of all, that the muscle activation is depending on task and on workload. We expected that to some extent, but we saw it very clearly, for example, on the forearm activation. Here you have in blue and in red, they are kind of superposed, okay, but you can see the general trend. The activation, the muscle activation in two muscles in the forearm. One is a wrist extensor, and another one is the flexor. So they are antagonists. They do opposite work, but their activation go together. Okay, especially in the last part, which is near to the deck landing, okay, the final touchdown. And this means that the co-contraction of these muscles is augmenting as the test progresses. And so in the most critical part of the test, the activation, total muscular activation in a part of the, most close to the controlling sector is increasing. And that means that if we then estimate the dynamic fit-through of the pilot, this is changing because the total muscular activation is changing, okay, the way the muscles respond in that particular case. What we did was to gather the measured data for the kinematics of the with the motion capture system, or the upper limbs, sorry, with the motion capture system, applied it to our models, and then our model, and then estimated various time steps during the reproduced test, simulated test, the biodynamic fit-through. And you see that when we go closer to touchdown, which is the yellow curve here, the damping of this curve is clearly changed, and also the natural frequency is clearly changed. In this case, since Andrea was very experienced in doing such maneuvers, the damping is increased. So we think that this is due to the experience of the pilot. It can manage to add more damping when it's needed, and the phase of the maneuver is the most critical. But the main output here was that task and workload is strongly affecting the biodynamic. So to progress further on these topics, what we are currently embarking is this major project, which is called, with touch of Italian creativity, Rotorcraft pilot couplings. project with Leonardo helicopters, which is a 3.5 years project. Total budget is 2.5 million, entirely provided by Leonardo. And we're building, actually, we are close to completing we are performing the first tests on the test bench, which is composed by a 6 DOF 1.5 tons of maximum payload motion platform, on which we built a reconfigurable cockpit, reconfigurable, sorry, in the sense that we can move the pivot points for the inceptors, lengths of the inceptors, and to represent basically whichever machine we want to test. Right now, the only interaction with the simulated, let's say, task is a glass cockpit, but we plan to insert more specific scenarios. And the goal here is to, first of all, experimentally validate our procedures for biodynamic characterization, actually to enhance the validation, because a lot of it has already been done in previous experiences. The analysis of adverse species scenarios, in the sense that we want to eventually simulate specific scenarios, but also for trigger events, and enhance in general our numerical model, with the final goal though being that of developing specific design recommendation. We want to move to the next phase, which is give specific recommendation to the design of new machines to avoid such problems. We are now in the final end of the second year of the project. We had some delay due to COVID, not just, but also COVID. And we hope that to get into the hot phase of the tests very soon. So with this slide, I have concluded, and I thank you for your kind attention. If you have any questions, we will be back.